Jai to all. Today I am here to deliver the fourth lecture of the fluid mechanics. In the previous lecture, I have discussed the various types of fluid flow and general problems based on that type of fluid flow. Okay. Now in this lecture, I will discuss here equation of motion, Euler's equation of motion, Bernoulli's equation from Euler's equation, Bernoulli's equation for real fluid, and practical applications of Bernoulli's equation, expression for rate of flow through the velocimeter, and last slide will be reference. So let us move towards the first slide. Equations of motion. So as per Newton's law Newton's second law of motion, F is equal to mass into acceleration in particular direction. Means total force in a particular direction can be written as mass into acceleration in the same direction. That is F equal to m into a. In the fluid flow, the following forces are present. During the literature review, it is confirmed that in the fluid motion, the following forces play a crucial role. That is the gravity force, the pressure force, force due to the viscosity, force due to the turbulence, and force due to the compressibility. These all forces are very effective during the fluid motion. Okay, so if we consider the combined effect of these forces, then we can write it as total force F equal to Fg. Fg means gravity force, Fg in particular direction, that is x direction, plus pressure force, plus viscosity force, plus turbulence force, plus compressibility force. Means total force will be the combination of all these forces. Okay. Now, what are the conclusions derived from this equation? If the force due to compressibility, that is the Fc, is negligible, the resulting net force Fx will be equal to the Fgx plus Fpx plus Fv plus Ftx. Okay, and the equation will become to Fx equal to Fg plus Fp plus Fv plus Ft, and these equations of motion are called Reynolds equation of motion. Okay, so in case of Reynolds equation of motion, only force due to compressibility are not considered. Okay, now the second conclusion is that if the force due to turbulence is negligible, then the resulting equations of motion are known as the Navier-Stokes equation. Okay, in case of Navier-Stokes equation, only force due to turbulence is negligible. Now the third conclusion is, if the flow is assumed to be ideal, then in that case viscous force, that is the Fv, will be zero. Okay, and the resulting equation of motion is known as the Euler's equation of motion. Okay, so there are three conclusions are derived from the total this equation of motion. First is the Reynolds equation of motion, in which force due to compressibility is negligible. In the second case, force due to turbulence is negligible. In that case, the equation of motion is known as the Navier-Stokes equation. And in the third case, that is when the force due to viscosity is negligible or zero, then this type of equation of motion is known as the Euler's equation of motion. Okay. Now, Euler's equation of motion. So, in case of Euler's equation of motion, we have earlier discussed here. In this case, force due to viscosity will be zero. Okay. Now, we have to derive here the Euler's equation for motion. Now, consider a fluid element of length dx and shape will be cylindrical. Then there are two phases. This is the first phase and this is the second phase. So suppose the flow of fluid is in this direction as shown in figure, then there will be forces acting at these two phases. the force acting at first phase will be P into dA. dA is the cross sectional area and small p is the intensity of pressure. Okay. Similarly, at phase 2 the force will be P plus del P by del S into ds bracket close into dA. So this term will be increment during the motion of fluid after the distance traveled by the fluid up to length ds. So this term is the additional gain in the force value. Okay. Now let us consider a streamline flow which is taking place in particular direction, that is S direction, as shown in the figure. Now, if the element is cylindrical, then its cross-sectional area dA and length ds is considered. The overall forces acting on the cylindrical element are: the first, that is pressure force at surface A or work will be P into dA in the direction of flow. Second, pressure force at the second surface will be P plus del P by del S into ds into dA, opposite of direction of flow. And third force will be weight of element rho g d a s. Okay. So this is the weight of this cylindrical element will be act downward, vertically downward. The value will be rho g dA into ds. Okay. Now in this figure the forces are acting and the directions are shown here. Now theta is the angle between the direction of flow and the line of action of the weight of element. Then the resultant force on the fluid element in the direction of S must be equal to the mass of fluid element into acceleration in the direction S. Therefore, the resultant force will be equal to, in this direction, that is direction of flow. So what will be the resultant forces? Let us consider this positive direction. So P into dA minus this value minus weight acting. So weight acting is vertically downward and its component will be in this direction. So this value will be cos theta, rho g dA into ds into cos theta, and this will be equal to the force into acceleration in particular direction, that is x direction. So force will be mass into acceleration in particular direction, that is the rho dA into ds into acceleration in s direction. So further, if we consider the value of as is the acceleration in the direction of s. As is the acceleration in direction of s. As is represented here. So as can be written as dv by dt. Okay, where v is a function of s and t. Further, dv by dt can be written as del v by del s into ds by dt plus del v by dt, or this can be further written as v into dv by ds plus dv by dt, as ds by dt can be written as v, velocity. If the flow is steady means constant with respect to time, means the flow characteristic does not vary with respect to time, then in that case del v by del t will be 0. So put the value of del v by del t equal to 0, then further as will be equal to del v by del s. If we put the value of as in equation number 6.2, then the final outcome will be minus del p by del s into ds into dA minus rho g dA ds cos theta equal to rho dA ds into as will be equal to v dv by del s. Okay, or further if you convert it in easier form, then it will become equal to del p by del rho into del s plus g cos theta plus v del v by del s equal to 0. Okay, further if we consider this element shown here, this length is considered as ds okay, and this height is dz, and angle made between these two parameters are theta. So from this angle, this triangle cos theta is equal to dz by ds. Okay, so let us use this term cos theta equal to dz by ds, and it will be replaced in the previous equation cos theta. Therefore, the final value will be 1 by rho dp by ds plus g dz by ds plus v dv by ds equal to 0, or further dp by rho plus g dz plus v dv equal to 0. Okay, or dt by rho plus g dz plus v dv equal to 0. This will be the final result, which is known as the Euler's equation of motion. Okay, so Euler's equation of motion can be obtained from the general equation of fluid motion by considering the viscosity forces as 0. Now, Bernoulli's equation from the Euler's equation. So how one can derive the Bernoulli's equation from the Euler's equation? So let us consider the equation number 6.3. If we integrate it, then it will become as the integration of del p by rho plus integration of g dz plus integration of v dv, and it will equal to the constant, because the integration of constant value will be equal to 0. So now if the flow is considered as the incompressible, okay, means fluid is considered as the ideal case, then rho is constant, therefore rho can be taken out from the integration symbol, then it will become equal to p by rho plus gz plus v square by 2 equal to constant. Okay, or further it can be written it as p by rho g plus z plus v square by 2g, means further these all terms is divided by g by v, so it will become equal to p by rho g plus z plus v square by 2g equal to constant, or in the most simplified form it can be written as p by rho g plus v square by 2g plus z equal to constant. So this is the equation of Bernoulli's equation from the Euler's equation. These three parameters have their individual significance, and individual terms can be further represented as the P by rho g equal to pressure energy per unit weight or pressure head. So P by rho g is simply known as the pressure head or pressure energy per unit weight of the fluid or liquid. Okay, V square by 2g is known as the kinetic energy per unit weight or kinetic head. Okay, similarly Z is known as the potential energy per unit weight or potential head. So what are the various assumptions made during the derivation of Bernoulli's equation from the Euler's equation? The first assumption is the fluid is ideal, that is the viscosity force is 0. Second is the flow is steady, means the fluid characteristic does not vary with respect to the time. Okay. Now the third assumption is the flow is incompressible, means density is constant. Okay. The flow is irrotational, means fluid flow does not rotate its own axis around its own axis during the fluid motion. So these are the basic assumptions were made during the derivation of Bernoulli's equation from the Euler's equation, which are very much essential to learn and remember. Now let us discuss a general problem based on the previous derivation. So in this problem, water is flowing through a pipe of 5 cm diameter under a pressure of 29.43 Newton per centimeter square, and this value is known as the gauge pressure, and with mean velocity of 2.0 meter per second. Find the total head or total energy per unit weight of the water at a cross section which is 5 meter above the datum. So in this problem we have to calculate the total energy P divided by rho g plus V square by 2g plus Z. So we have to calculate all these three parameters and then sum these values. You will get the total energy head. Okay, so let us consider the given values. Diameter of pipe is given as 5 cm, it will equal to 0.5 meter. Pressure value is given here 29.43 Newton per centimeter. So you should convert it in SI system. Then the value will be 29.43 is to 10 raised by 4 Newton per meter square. Unit is very essential. One should always focus on it. Okay. So velocity is given for the 2 meter per second. So it does not require to change its unit because it is already in SI system. Okay. Datum head, that is the Z equal to 5 meter. So total head is can be written as pressure head plus kinetic head plus datum head. So let us consider individual value. Pressure head can be calculated using P by rho G. So P value is given here. Rho is the standard value in case of given fluid. If fluid is mentioned here, then the value is given. So fluid is water, means value will be 1000 kilogram per meter cube in SI system. So put this value, and G has a standard value. So further if you solve it, then pressure head will be 30 meter. Okay. Similarly, kinetic head can be calculated using V square by 2G. V is already given here, 2 meter per second square. So put these values V and G. So it will equal to 0.204 meter. So pressure head and kinetic head is already calculated. Now the total head, it will be obtained using the sum of these two, and further datum head is already given 5 meter. Okay. So putting all these values, you will get the total head, that is the 35.204 meter. Okay. So in this problem, what are the total energy head? It will be equal to 35.204 meter. Okay. So it is very simple question based on the formula. Now the second question is a pipe through which water is flowing is having diameters 20 centimeter and 10 centimeter at the cross sections. Means this is the 1 cross section and this is the 2 cross section. So on this cross section, the velocity V1 and D1 is given here. At section 2 diameter is given, but velocity is same for both these sections. Okay, as per the given question. Now find the velocity at the velocity head at sections 1 and 2 and also rate of discharge. Means we have to calculate at V1 square by 2G at section 1 and velocity square by 2G at section 2 and rate of discharge means capital Q. Capital Q is E1 V1. Okay. So rate of discharge is also need to be calculated. So put all the given value. D1 equal to 20 cm will be equal to 0.2 meter. Area of cross section 1 will be pi by 4 D1 square because it is circular. So it will be equal to 0.0314 meter square. V1 will be 4.0 meter per second and V2 is given 0.1 meter. Similarly, A2 can be calculated pi by 4 D square with dt square. So it will be equal to 0.0075 meter square. Now velocity head at section 1 can be calculated using V1 square by 2G. Put the value of V and G. So it will be equal to 0.815 meter. Okay. Similarly, velocity head at section 2 will be given as V2 square by 2G. Okay. And how one can calculate the value of V2? In question there is missing value of V2. So you need to use the continuity equation. So continuity equation क्या कहता है? Continuity equation E1 V1 equal to A2 V2. So using this formula, one can calculate the unknown parameter. So using the continuity equation, V2 can be calculated as A1 V1 upon A2. sorry. So putting all these values, that is the A1 B1 divided to, it will be equal to 16 meter per second. So V2 is the velocity at section 2, 16 meter per second. So now we can calculate the velocity at section 2, V2 square by 2g. So final value of V2 square by 2g will be 83.047 meter. Okay. Now rate of discharge. So already I have discussed here, the rate of discharge at any particular section can be given as a area into average velocity, cross sectional area at that section and average velocity at that section. Okay. So A1 V1. So put the value of A1 V1, or you can also put the value of A2 V2. So the final value will be 0.126 meter cube per second, or you can convert it into liters per second. So in liters per second it will equal to 125.6 liters per second. So these two examples are based on the derivation, that is the Bernoulli equation. Now what will be the equation for the Bernoulli equation? In case of fluid is real, that is a real fluid. So in case of real fluid, there is no incompressible fluid, means all the fluids are compressible, means in that case density does not remain constant. Okay, so let us discuss. In the Bernoulli equation, as we derived the assumption that the fluid is inviscid, that is non-viscid. Okay, and therefore the frictionless, but all the real fluids are viscous and hence offer resistance flow. So there are always some losses in the fluid flows, and hence in the application of Bernoulli's equation, these losses have to be taken into consideration. Therefore, the Bernoulli's equation for real fluids between points 1 and 2 means, suppose this is a 5, okay, and section 1, section 2, okay. So fluid is passing through these two sections. So if the fluid is real, means there is a force of viscous force will be also effective, which resists the internal forces. Okay. So in that case, some fluid energy is losses. Okay. If the fluid is starting to flow from section 1 to 2 and it comes out from section 2, then we will observe that there is a lesser energy at section 2 as compared to the section 1. Okay, so this is due to the head loss. Therefore, in that case, the Bernoulli's equation, which has been already derived, can be further written as P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL. This additional term HL is the loss due to head loss. Okay, loss due to viscous force resistance. Okay, where HL is the loss of energy between points 1 and 2. If the fluid is same, that is the density will be equal, that is the rho and rho, means at this section density will be same at this section. Okay, let us consider a simple example based on this equation. A pipe of diameter 400 mm carries water at velocity of 25 meters per second. The pressures at the points A and B are given as 29.43 Newton per centimeter square and 22.563 Newton per centimeter respectively, while the datum head at A and B are 28 meter and 30 meter. Find the losses of head between A and B. Means we have to calculate the value of head loss. Okay, so we have to use the same formula. That is this formula. Let us discuss. So this is the general diagram. This is the section 1. Okay, and it is inclined at some angle. So this height, that is the this height from the baseline, that is datum line, is ZA, and this point B is above from the datum line at the distance at the height of ZB. Further, at section 1, that is point A, DA is given 400 mm, pressure is given, and ZA value is given. In the same way, at section 2, diameter at point B is given, pressure intensity given, and datum at ZB is given. So if we further apply the formula of total energy at point A, then you can write it as EA equal to PE by rho g plus VA square by 2g plus ZA. So put all the values given here. PA is given, VA is given, ZA is given, and density is already the standard value as in case of water. So putting all this value, you can get the total energy at point A. It will be equal to 89.85 meter. Now at point B, pressure, datum head and velocity head is already given. So using the total energy formula at point B as in case of at point A, you can further put all this value. The value of total energy here can be obtained as 84.85 meter. So if you carefully observe the total energy at these 2 points, that is point A is 89.85 and at point B it is calculated at 84.85, means there is a loss of energy at point B as compared to point A. So this loss of energy due to the head loss. So loss of energy can be finally calculated as total energy at point A minus total energy at B. So it will be equal to the 5 meter. So the loss of total energy here in case of fluid moving from point A to point B is equal to 5 meter. Is it clear? Okay. Now practical applications of Bernoulli's equation. So in general, the practical application of Bernoulli's equation are applied during these instruments, that is the benturimeter, orifice meter and pitot tube. Now in case of benturimeter is used for measuring the rate of flow of a fluid flowing through a pipe. So benturimeter can be used to measure the rate of flow of fluid through a pipe. Okay, it consists of 3 parts as shown in figure. This is the diagram for the benturimeter taken from the article. Okay, so in this figure, as you can easily see here, that the benturimeter have its different parts. The first, that is the short converging part. This part is known as the short converging part. Okay, and from this side water is entering, that is the inlet point, and this is the outlet point. Okay, so this portion is known as the short converging part. Okay, next this portion is known as the throat, as shown here, throat, and the last portion, that is this portion, is known as the diverging part. Okay, so it is based on the principle of Bernoulli's equation, means benturimeter is based on the Bernoulli's equation. Now let us discuss the expression for rate of flow through the benturimeter. So suppose D1, T1 and V1 are the respective parameters at section 1. Okay, so area at section 1 will be equal to the pi by 4 divided square. In the same way, D2, P2, V2, A2 are defined at section 2. So suppose if you apply the Bernoulli's equation at these 2 sections, then you can easily write it as P1 by pressure energy at section 1 plus velocity energy, kinetic energy at section 1 plus datum head will be equal to the pressure energy at section 2, velocity energy at section 2 and datum head at section 2. Suppose pipe is horizontal. Suppose a pipe is considered here and this is horizontal. This is the base or datum line. Then the height will be remain constant. Okay, so in that case Z1 will be Z2. So further equation can be modified as P1 by rho g plus V1 square by 2g equal to P2 by rho g plus V2 square by 2g, and further if you further simplify it, then it will be equal to P1 minus P2 by rho g equal to V2 square minus 2g minus V1 square by 2g. Further, if you sort it, then P1 minus P2 by rho g can be written as the difference of pressure at section 1 and 2, and further it can be represented as small h, and small h can be represented as Vt square minus 2g, Vt square by 2g minus Vt square by 2g. Okay. Now after this, if you apply the continuity equation at section 1 and 2, then you can write it as a1 v1 equal to a2 v2 or v1 equal to a2 v2 by a1 square. Further, if you put the value of v1 square, then the final equation will be, if you simplify it, then the final value will be equal to v2 is equal to a1 by square root of a1 square minus a2 square into square root of 2g. So discharge Q can be written as a2 v2, and putting the value of v2, this value, then it will be equal to the a2 square, a1 a2 divided square root of a1 square minus a2 square into square root of 2g. Further, this equation is the ideal condition, discharge under ideal condition. But in case of theoretical discharge, actual discharge will be lesser than the theoretical discharge. So in case of actual discharge, it can be represented as the CD, coefficient of discharge, is a constant term into E1 A2 divided by square root of A1 square minus A2 square into square root of 2g. So this is the general formula for the H value. H can be calculated in different cases. For example, if the differential manometer contains a liquid which is heavier than the liquid flowing through the pipeline, then H can be written as X into SH by S0 minus 1. SH and S0 X is already defined here. In case of second, if the differential manometer contains a liquid which is lighter than the liquid flowing through the pipe, the value of H can be written here. Okay, so H can be calculated in the corresponding cases. Okay, and this is the general equation. You can calculate general problems based on the previous equation. You can try it at home. So this is the references where I have taken my study materials for these lectures. Thank you to all. So we will meet at next lecture. Thank you.
Very good.